begin with, there is a charged particle which enters a region in which there is a frictional force proportional to particle's speed. So basically, there is a drag force acting on this particle, right? So it was observed that the particle travels for 10 centimeter. Let me call this distance as S0. And according to the diagram, this is the distance S0. I mean, it started from this point I, it ended up here, final first, and the distance it traveled is S0, right? Now remember, I have taken gravity in the cross direction in this problem, and between the particle and the table, there is drag force, and drag in this problem is somewhat like minus kV vector. Okay. Now, second time what happens? Now he repeats the experiment. This time there is a homogeneous magnetic field also which is present perpendicular to the plane of the trajectory in the cross direction, and let's say that the field is B. Now he has observed that if he throws the particle again, the particle follows a different trajectory and stops at some point whose distance from the starting point is 6 centimeter. Call this distance S1. So basically this line has got a length of S1, right? And now for the third time, again he throws the particle here, but now the magnetic field has been made 2B. It follows a third trajectory, which is similar to the second one, but not the same. And it stops at a point whose displacement from the starting point is S2. The question is, nothing is given, only S0 is given, S1 is given. Can we find out if the given terms are S0, S1? Can we find out the expression of S2? Can we find out the expression of S2 in terms of S0 and S1? That is the point. And remember, I don't want to derive the complete equation. I want to look into the pattern and comment on the answer. What I'm trying to say is, if you look into the 3 steps, let's say I observe the step 1 of the problem, step 1, and just look into the impulse equation directly. So what you could have said is, in the first case, if you throw this particle with U0, the impulse that you will get is minus K into V dt, and integral of this term should be the change in momentum from I to F, and that will be minus mu0. So we understand this distance is S0, integral V dt. So basically K S0 upon M, that is coming out as U0. That is my first equation. Now let us start the problem. Leave these basic things. Now think about the problem carefully. Actually, there's a very nice observation. The observation is, for path 2 or 3, if I go to a general location, we understand that the force which is acting is Q V cross B. So there is a Q V cross B term, and there is a minus KV term that is acting. Multiply this equation by dt. Multiply this by dt, that will give me a dp term here, dp. Now try to observe carefully. If you multiply this term dt with both the terms, this dt will come here in this expression. This becomes q into ds vector cross b, and minus k v dt becomes ds, and that becomes your dp. Basically, dp is this, right? I've taken this dt scalar with this v term. And now just I thought upon taking integral. So I think everybody was clear that minus the final momentum is 0. So minus mu0 I cap. This is q times, don't bother about this term. This is q times s vector cross b, the total displacement, because q and b are constants. And this will become minus k times S vector. This is my main equation, which holds for step 2. Step 2. This is the equation. The problem is, if now I start explaining or expressing all the terms in terms of I, j, k, and then I start solving, it will be a very lengthy exercise, which is not required. Now comes the important point in this problem. Because I knew that only S0 and S1 are given, and I had to calculate S2, what I should have done at this step should be, I should take the dot of this equation, dot product of this equation with the same equation. So the term that I am getting now is minus mu naught I cap dot minus mu naught. So I am having, observe, I'm having a m square u naught square term, LHS. Now just be very careful with RHS, what you will get. So these are the two vectors and dotted with the same one. Now expand the term. So one term that I will get is minus ks. So I will have a k square s dot s square term, right? I will also have in RHS, I will also have a q s cross b dot ks term. And now bड़ी obvious बात है that S cross B is perpendicular to S. So when you will take the dot product with S, it will become 0. So Q S cross B dot Ks, 0. Ks dot Q S cross B, that is also 0. So the only term left is Q S cross B dot Q S cross B. So basically, I have Q square S vector cross B vector, the mod square. That's what I'll have. So basically, my equation becomes m square u naught square is equal to k square s square plus the second term is q square. Now s cross b mod square. So that is s square b square. And remember, whatever is my displacement vector, that is perpendicular to b. So I'll have that sine 90 term. This is my general equation now. Because if this was my first equation, right? Here I have got my second equation. Just I have to divide this second equation by k square. If I divide this equation by k square here, remember k is also not given, and k square term I also take here. So LHS becomes m square u naught square by k square. So basically, s naught square becomes equal to s square plus whatever term you are having, which is, q square b square s square by k square. Now let me do one thing. Because I have written the second equation, I know b is b and I'm substituting s as s1 here. And symmetrically, when I will try to write my third equation, it will become s naught square. Now s term will become s2. So I'll have a s2 square term, and now b has become 2b. So it is q square 4b square s2 square divided by k square. Now you understand, because q, b, and k are not given, so you have to appropriately arrange. So I'm writing my final answer. What I will do, I will take S0 and S1 on one side. So S0 square minus S1 square on one side divided by S1 square should be equal to the second term that I will write is S0 square minus S2 square, and I will divide this complete equation by 4s2 square. That is 4s2 square. Now observe this equation very, very carefully. आप बंद कर दीजिएगा गेट बाहर से, बंद कर दीजिए. This is the key equation, and through this equation, the only unknown of the problem, S2, can be directly solved. You remember, I have not written the basic AX, AY. Generally, while solving such problems, students either try to get the answer directly through impulse, but if you observe this mechanism, I have never used the vector equation and I've completely focused on the data. So the only hitch here was, if you take the dot product with the equation, then you will get the scalar format of the equation, and the magnitudes of displacement will be involved here. S0, S1 given, S2 can be easily admitted. So that this was the point, and I think all of you will get the answer to the problem. The second problem in order was question number 166. Again, it's a very nicely built up problem, which is based on the Foucault pendulum, where the concept of magnetic force has been used. Just read the data of the problem carefully and we'll analyze it. The question says, there is a small ball of mass m, right? And this ball is carrying a positive charge of Q, and it is suspended by an insulating string of length L. The pendulum so formed is placed at rest in a homogeneous, now this is interesting. It is placed at rest in a homogeneous vertical magnetic field of strength V. Now the experiments have proved that if the ball is initially knocked, मतलब आप क्या करो, you take this pendulum and try to provide it a flick. So if magnetic field was not present, it will oscillate, simple pendulum. But if there is a vertical magnetic field, not only will it oscillate, the plane of oscillation will also rotate. Not only will the particle oscillate, the plane of oscillation will also rotate. And that is why he is saying, I mean, we have to justify why this is happening, how is it rotating, and then comes the actual question for J Advanced. How long does it take for the plane which is rotating to make one complete revolution? Very beautiful problem written by Nadig. And we have to observe it very carefully. The solution is even very different. So just stay with the problem. So it is oscillating like this, and there's a plane of oscillation, and the plane will rotate. Now let's see how. What exactly is happening? So let me, and all the assumptions of small angle are valid to make this problem symmetric with angular SHM for small theta. So to begin with, what has happened? This guy is there. इसके पास Q charge है. The mass M. Gravity is present. G. The length of the pendulum is L. Maybe a magnetic field comes into picture. So let it oscillate. No issue. Now tell me, if this guy is oscillating and I do have a magnetic field B, right, and I reach this position here, right, now because of V cross B, if it is going away with V, V cross B will also exert a force which is in the cross direction. So the problem now is that there is gravity which is providing me torque, restoring torque, and there is this V cross B which is trying to push my plane inwards. Now, one thing is clear, that there is one force, magnetic force, which will always try to change the plane of motion of the charged particle. Charged particle would otherwise have been in a vertical plane, but that plane itself will rotate because of the presence of magnetic field. We understood this point. Somebody said, sir, what is the fundamental equation which is governing the motion of this particle? So if I look into that fundamental equation, what are the terms I am having? I think mass of the particle is m, acceleration is, let's say, dv by dt. So I'm observing this motion. That should be equal to q v cross b. This force will act, q v cross b, always. And there will be one centrifugal term. I mean, it seems like there will be one term which is minus m omega square r vector. There will be this term which is m omega square r term. So basically I'm writing that term minus m omega square r vector. Let's understand that to begin with, it was oscillating in that vertical plane and omega ka value root g by L tha. And at every instance, जो टेंशन लग रहा था इसके ऊपर, that tension was being balanced by this force, na? I mean the horizontal component. So basically what I'm trying to say, this omega to begin with was root of g by L, and there was this force which was acting. So I've written this term. So practically that T which was prevalent, that mg term which was prevalent, the resultant of those T and mg I've inculcated in this minus m omega square r. So try to understand that these are the two real forces other than this, which I have written through this expression m omega square r ka negative, right? Now, the problem is, how can we solve this equation or this differential equation to obtain my final result? Now comes the important part of the problem. Now what will I do? For a moment, I will leave this combination as such, and I will discuss another mechanical situation which is absolutely similar in terms of vector equation with the situation in hand. So what is that situation? Now that's why I use that term Foucault pendulum. What was that situation? So forget the name Foucault pendulum, observe the situation. The situation is, you take this pendulum which is oscillating. Forget this question and think about a new question now. Take a pendulum which is oscillating, there is no magnetic field. Now do one thing, you start observing this pendulum from a rotating frame of reference which is himself rotating with an angular velocity about this axis. So if this is my pendulum in the new situation, right, and this is the axis, and I am myself rotating with the angular velocity, I'm using a new omega vector about the axis, then what will I observe? Now, because I am coming outward, I'm spinning with this angular velocity omega, I will observe that this pendulum has got an anti-capital omega vector. Basically, in this motion, there was no change of plane of motion, but I hypothetically generated that situation because I started spinning myself in a direction which is outward with the angular velocity omega vector. So I observed an anti-omega for this particle. And now when I observe that, what is the equation I will write for this particle? So I thought, again, if the particle is having a mass of m in this hypothetical situation, why I'm generating this hypothetical situation? Because then the mechanics of this hypothetical situation will be known to me, and I will map that situation with the given situation and problem will become simple. I will also tell you the thought process through which I realized that I should do that. You are understanding one thing, that why I would have rotated with omega outward, because I wanted to provide it anti-omega which is similar to the motion because of V cross B. One thing is very simple. So now what I should have written? I would have written mass into acceleration term again, dv by dt. Now let's see in RHS, what are the terms I will write for that particle. So the first term that comes to our mind is the Coriolis term. So the Coriolis force term will be minus 2m. It is minus 2m, right? It is m into minus 2 omega vector cross VREL vector, and that term will become V now. So, I mean, this term as such becomes twice of m omega vector. I mean, if you have taken that minus term separately, so you'll have that V vector cross capital omega vector term. Have you all लिखेंगे? So 2m V cross omega will come. Then comes the real force term. So I'm using the one term which is minus m omega naught square into r vector. Try to understand that this term represents the real force. The real force which was present in the problem when it had angular frequency omega naught, quite similar to what I have written here. That term is again present here. Only thing is that angular frequency in that problem was omega. Here it may have a different value. Let us see whether it gets the same value or not. That term I have taken as omega naught. And the third force will come because of the centrifugal thrust, and that is m capital omega square into r vector. If you observe carefully, you'll have a m capital omega square into r vector. Let me repeat what are the three terms that I have written here. While writing mass into acceleration, this is, let's say, my equation number 2. While writing mass into acceleration, I have written all the real forces. Those real forces, because actually I am rotating with omega, na? That's why I'm writing two extra terms. Otherwise, the real forces were only minus m omega naught square r vector. And these two imaginary forces are, we have studied them, the Coriolis term, the centrifugal term. Now, the question should be done by comparison of these two situations. Compare these two situations. Think that what you have done here in terms of capital omega makes this equation absolutely identical with what is happening here. How come? Check. Here, it seems like, after comparison, that 2m omega vector is resembling your QB vector, QB vector. I'm interested in the mod of this term. So my omega mod comes out as QB by twice of m. That is the first thing that comes up here, first thing. And also, the second star equation that I can write is minus m. So basically, minus mr. So omega square here will become omega naught square minus omega naught square minus capital omega square. So I said this thing categorically. What is required is omega naught. Omega naught comes out as plus minus root of small omega square plus capital omega square. Negative is not possible. So basically root of. Remember, this small omega square term is G by L, and this capital omega square is Q square B square by 4m square. Examiner can definitely ask this value of omega naught also in the problem. And other than that, if I just observe his question was simply, how long does it take for the plane to make one complete revolution? Now, because you are rotating with capital omega, right? So you can see the time that it will take for complete, the answer should be 2 pi by capital omega. And we have categorically calculated capital omega. So it seems to be 2 pi by QB by twice of m. So basically it comes out as 4 pi m upon QB. As far as the answer to the question is concerned, that will come out as 4 pi small m by Q into B. And if you look into that omega naught is the actual angular frequency of pendulum. In the actual situation, you understood that this capital omega was just a mechanical method of, converting this simple pendulum problem observed from a rotating frame of reference to a problem where there is no change of frame of reference. Rather, in the practical situation, there was a pendulum along with the magnetic field, which is similar to this question. And because this question was very straightforward for me, by writing two additional virtual forces, I just mapped the real force equation here and here. And by comparison, I got that omega. That was required also, no? That was the only requirement. And how come this idea comes here? So the idea was very obvious that there is one oscillation and one into the plane motion, which depends upon this term. Now, into the plane motion, perpendicular to the velocity, is very similar to the term of Coriolis force. That's what it does. Coriolis deflection is symmetric, I mean, sideway deflection, which is happening, and the proportionality with velocity was also the same. So it was very similar in physically. So this is the easiest way of mapping this problem and using that result, because already I know the value of omega. Omega naught is the only unknown. In a multi-correct, they can put up a question where they can ask omega naught, which we can find out here. And even if they ask the time that it will take, that can also be depicted. So whenever you are solving problems where this term QV cross B is coming and rotation is happening twice, I mean, rotate ho raha hai, and again rotation of the plane in which it is revolving, you should think in terms of Coriolis. If you can map your magnetic field to some Coriolis term, then the problem may become easy. So that was the core idea of the problem. The problem says that, you can read it, this problem investigates the motion of two electrons that are moving in a plane perpendicular to the field lines of a homogeneous magnetic field. The electrons are considered classical point masses, fine, affected only by electric and magnetic forces. Now, the first part of the question, a standard JEE problem. The two electrons initially at rest are at a distance small d. Then they are given initial velocities of identical magnitudes but opposite direction. So, आपको ये बताना है, what is the condition on the distance between them in the subsequent motion if the separation between the particles has to remain constant, and you need to derive for the expression of V also. So let me take gravity-free space and let me take these two electrons minus E kept at some distance d, and these guys are to be provided with velocities in the opposite direction. Now, and there's a magnetic field also. So first thing that comes to my mind, let's presume magnetic fields. Let's say magnetic field is in the cross direction B. Remember one thing carefully, when in problems on magnetic field or magnetic force, you make statements on center of mass, you have to be careful because there is this external B which is coming now, and the generator of that field, some moving charge, is not a part of the system. That is not a part of system. So it cannot be called upon as a closed system with magnetic forces being internal. It cannot be called upon like that. What should I do then? Okay, electrostatic interaction is fine. So they will repel with Fe. That was fine. One thing that comes to my mind, simplest thing, if they have to have that constant distance and B is like this, so I think if I provide velocities which is perpendicular to the line joining them in an appropriate manner, such that that force comes inwards, if I can generate Fm andar ki taraf, Fm here also, it may serve the purpose. So let me take that V up and let me take a symmetric V down. So V cross B term and charge is negative. So as far as this problem is concerned, if I make my Fm minus Fe as M, M is the mass of electron. So M into V square upon D by 2, my first equation, where Fm is EVB. Stay with the problem. The second part is very nicely built up and it will take a lot of ideas to sort it out. This was the starting part, or ye to theek hi hai. It will become K electrostatic into E square divided by D square. As far as this part is concerned, it is a quadratic. Solve this quadratic in V. Solve this quadratic in V. So let's see. It is EV by B minus KE square upon D square. And that is 2ME V square divided by D. So what happened? Let me multiply. So E V D square minus K E square B is equal to 2 ME V square D D D B. So what happened? 2 ME D B V square minus E D square V plus K E square B, that comes out as 0. And now there are a few things that come to my mind. If I make that discriminant, I mean, it is E square D4 greater than equal to 4 into 2 ME DB into K E square B. So if you solve this equation, that D comes out to be greater than equal to, solve it, it comes out as cube root of 8MK upon B square. It is cube root of 8K into M term, ME term or M term divided by B square. Now, the point is, ठीक है, इसने बोला था, what is the value of D min? So the condition on D is this. This is the minimum D at which they can be kept. And remember, I mean, it is possible that if you have anything less than this D, then you can't even find out any velocity with which you can sustain this situation. You can't. It is not possible for the particles to stay at a constant distance. But other than this D, if you take any value of D, for every D, you will have two possible V values. In the same direction, there are two possible V's. I mean, any value you can throw with, and it will move on a circular path. So, and he said, what is the expression of V? I have already said, you give me D, I will give you V. So V is the root of this equation, and there are two possible V's. So two possible V's. Fine. Now comes the actual problem. Now what he wanted in the B part of the problem, the important combination, here he was clear. He said, I want to keep one particle at rest and I want to throw the other one. And I'm more interested in the analysis of the problem. Just read it carefully. He said, show that. Now we will start it from scratch. It is again possible to maintain a constant separation if only अगर एक इलेक्ट्रॉन को वेलोसिटी दूं और एक को दूं ही नहीं, still it is possible to maintain a constant separation D. This is something that we have to prove. And if this happens, what is the trajectory of the center of mass of the system in this case? Remember, in the previous problem, the center of mass stayed at rest. The only reason there was the external magnetic field is applying the two magnetic forces in such a way that it stays at rest. But that is not a general result. Generally, I would not have said that, but that was a special combination. Now, here, if you have to maintain distance, the question setter is saying that center of mass won't stay at rest. It will follow some trajectory. Derive the equation of the trajectory. So that is the second thing. And the third thing again is what is the minimal distance that is necessary to realize this kind of motion. Last way, it is a qualitative problem. He also said that sketch the trajectories of electron in that case. And also tell me, very interesting, last problem, when will the initially moving electron stop for the first time? So lengthy problem, I will go step by step to solve this problem. First of all, let us try to understand that if these two people are kept at positions R1 and R2, let's say, let's say, I'm randomly solving it. If this was my origin, I have one guy kept at a position vector R1, the other person, you have to stay with the problem because the final result is very nice. So I need to derive that first. So maybe minus E, one electron here, one was here, and there is a magnetic field also, B vector, which is perpendicular to the plane, the same idea. So if you want to write the general equation for particle 1 and for particle 2, what will I say? Now I'm using m. So m into a1 mass into acceleration of particle 1 is a electrostatic repulsion between them and q v cross b. Now remember that q v cross b is minus e term times v vector cross b vector. For the first particle, call it v1. And what about that force between them? So it is k e square upon r cube. So that is r1 vector minus r2 vector, the mod cube into check what is the direction. Repulsion is this. So r1 vector minus r2 vector. K e square upon r1 minus r2 mod cube, r1 vector minus r2 vector, and q v cross b, and q term there was minus e. Now try to observe that if you write the same equation for the second particle, there the terms that I'll have is this term will be symmetric with a R2 minus R1 here. And here I'll have Q, velocity will be different, which is V2 vector, and we cross this with B. These are the two equations of, these two terms here, Q V cross B, Q V cross B. This constant is fine. Same, K E square upon R1 vector minus R2 vector mod whole cube. Remember, because now as both of them are having the same masses, the R coordinate, the position vector of center of mass is always R1 plus R2 by 2. Few things I can write. I also know their VCM always, because he has said find the trajectory of center of mass. So now I am coming to the core idea. It is V1 plus V2 by 2. I think all of you can understand this point that so much of problem is coming because of magnetic field. Otherwise, generally, if the person who is generating field and the person on whom it is being acted upon are a part of system, then the force will cancel. But here it is not the case because the generator B is outside the system. That is where the problem lies. And if somebody simply puts up the question, I cannot make direct comment. That's why I have to go through all this. So I know this thing that ACM was equal to A1 vector plus A2 vector divided by 2. And here this term will be simple because now if you add these two equations, check, this term will cancel. So basically in this equation, m into A1 plus A2 actually comes out as minus E times V1 plus V2 crossed with B. V1 vector plus V2 vector crossed with the magnetic field B. That's what I'm getting. And divide by 2 here, divide by 2 here. Now, this tells me that in this problem, mass into acceleration of center of mass is like a charge minus E moving with the velocity of VCM under the effect of the magnetic field. That is what I have proved. इसका मतलब मैं ये बोल रहा हूँ कि सवाल की जो इक्वेशन है MA, वो ऐसी है जैसे सेंटर ऑफ मास पे, जैसे सेंटर ऑफ मास के ऊपर some hypothetical, actually it is minus c, it is minus c, but on the center of mass there is a hypothetical minus c. If I assume that there is a hypothetical minus c moving with velocity of center of mass in the magnetic field, then the force that that particle, मतलब this guy will feel, उसकी वजह से whatever motion of center of mass will come, that is the actual motion of center of mass. And now life becomes very easy because this tells me that center of mass will move on a uniform, in a uniform circular motion, because center of mass is under the effect of B through this equation QV plus B, and B is perpendicular to the plane. Anytime in the actual motion, the motion will always be perpendicular to plane of, it will be in a plane which is perpendicular to B, because B cannot generate any motion along itself. And the charges ke beech mein jo repulsion or whatever is happening, that will also lie in this plane. So I am very clear that center of mass is moving on a uniform circular motion. So answer for the first part is this. What are the results? I mean, what is the omega of center of mass? So we can write all the terms. Remember, this m here represents the mass of electron. Don't think like this, that I am replacing the mass m by 2m here, minus c by minus 2e here, and when I take the ratio, it cancels. There is no such logic. It's only about the physics of the problem, which is telling such a nice, wonderful relation, that the relation of forces is such that when you add up, this cancels, and this can happen every time. Whenever the common force between charged particle will cancel, then only this will remain, and this becomes similar to that of a motion of one particle which is kept at the center of mass. And because in this case it would have been a uniform circular motion, so it will possess uniform circular motion with omega, which is alpha b, which is E by m from this equation multiplied by b. This is the angular velocity of uniform circular motion which center of mass will possess, and it will also move on a circle whose radius is RCM. This is again interesting. It will move on a circle whose radius is RCM, and RCM will be equal to VCM by omega Cm. So you understand, omega Cm comes out to be EB by m. VCM is required. So in the beginning, if you provide one of them a velocity v, and one of them you don't provide any velocity, so VCM in the beginning will be v by 2. If you provide one guy 0 and the other guy you provide v wherever, then VCM in the beginning is v by 2, and that cannot change because center of mass is moving in a uniform circular motion. So whatever is the speed of center of mass at t is equal to 0, that will be sustained. So the radius on which center of mass moves and the omega with which center of mass moves, that is known to me. This is one part of the question. Still, the bigger question remains that what will the particle do now? Actually, this is beautiful. Center of mass will move on a circle, and about the center of mass, again, they will start moving on circle, something of that sort. Now let's see, how can I define the motion of individual particles now? So now, I'll go back to the combination again. Now I am entering the second segment of the problem. Now, again, take your particle 1, general T, right? Somewhere, this guy 2 somewhere, and there is this center of mass having position vector RCM vector. One thing is very clear, this is origin. This is center of mass, his path is known. One thing is clear, with respect to center of mass, if I know this thing, this vector and this vector will be opposite, no? So if this position vector is R1 vector, and here the position vector is R2 vector, I'm deliberately taking this guy as my as my RCM vector. So you know that these two vectors are equal and opposite. Name them something. I mean, take this vector as R and this vector as minus R, and remember they are variable vectors. So I have taken R1 as RCM plus R vector, right? And R vector here comes out as, what is this coming out as? This is coming out as, let me write it properly, R1 minus RCM, and because they are equal masses, this is simply R1 plus R2 divided by 2. So what comes up is R1 minus R2 divided by 2. So you know, with respect to center of mass, his position vector is this. And the other guy, this minus R, is the negative. So this is R2 minus R1 by 2. Now, fine. Now let us try to work out the equations in this problem. Now this vector represents the relative position of 1 with respect to 2, right? That is 1 with respect to center of mass. Okay, so just try to differentiate this term twice. Let's see what will you get. Because already the equations that I have written previously for A1 and A2, just observe, these equations will take me there only. Even if I would have subtracted these equations, what I would have got? My equation would have been M A1 vector plus A2 vector. Let's see what I am getting as my RHS term. So just try to subtract these two terms. You will have 2k e square term upon R1 vector minus R2 vector mod cube. What is in numerator? I'm having R1 minus R2 minus so twice of R1 minus R2. I'm having twice term. So R1 minus R2 term. That is one thing. When I subtracted, I got minus E times V1 vector minus V2 vector crossed with B. Just check this equation first before we move forward. M into A1 minus A2, 2k E square upon R1 minus R2 के mod का cube, R1 minus R2 minus this term. Everything seems to be fine here. Now try to observe this in context of R that I have written. Remember, you are understanding, I am trying to convert my differential equation into everything. Indirectly, I want to analyze this problem from C frame. And C, I know. So I want to study everything in terms of this R which we are writing. And I think we are clear here. These terms are clear. So replace things in terms of R vector. So R1 minus R2, you replace by twice of R vector, right? This is the position vector with respect to center of mass. A1, this thing was very clear that R vector comes out as R1 minus R2 upon 2. So I'm replacing R1 minus R2 by twice of R. And same thing I want to do hypothetically with terms like this term I want to write as twice of some A vector. Stay with this, what is A, I'll explain. And I want to write this term as twice of V vector. I mean, you can write 2 capital A, capital V, whatever. The point is, if you define that R1 minus R2 term, 2 is a constant which can be managed at the last step. So don't bother about the 2 term. Apparently, this equation is similar to the previous equation. Just observe. All these 2 terms will cancel out. And now if you look into this equation, why I have done this? This mathematical format is similar to what I have done in part A of the problem. एक बार सोचते हैं मैंने क्या किया था. In part A, I put mass into acceleration of one of them, any one of them. I got these terms 2k e square r1 minus r2 mod cube. बस वहां पर अंतर क्या था? If you write this equation as 2r, then even the denominator term will be replaced by 2r mod cube, effectively. So basically, if I start thinking that even in this problem, this point is fixed. The point which was fixed in the A part, that was center of mass. If I start observing this way, that this differential equation is same. Here also in part A, just observe. While I solve for part A, what happened in the problem? The term that you have got there, that is corresponding to a total distance d, which I am now thinking as 2r. If you are convinced with this small r, you are confused, you use this capital R term here, so that this minus capital R vector. I mean, I just want to compare this with the d by 2 term of first part. And looking into this equation and the similarity with that previous equation, this will help me out. Remember, R1 vector minus R2 vector mod I will replace by 2R vector mod. That's what I'm trying to say. And then the term 2 will obviously cancel out there. And effectively, this will become 2R. You will get ke square. I mean, you are understanding, I think. This is a ke square twice of R vector effectively. And नीचे clear है आपको that 2R vector के mod का cube. That's what we are getting. Ke square 2R vector upon 2R vector के mod का cube. And rest is simple, minus E times V cross D term as we have got there, right? And here also you have got the same M into A term. Just observe carefully that this equation is absolutely symmetric with A part of the problem. The only thing is now I'm writing it about the rotating center of mass. So qualitatively, his question was very clear. His question was, what is the motion that those two people will apparently have? Once I understand this equation, I can directly comment on everything as I have commented previously. Let's say previously my answer on D comes out to be, I'll check that result. My D, whatever D came out to be earlier, I'll have a symmetric D here. It should be root of, that was the cube root of 8km divided by that constant term. That constant term that came there was D square. Even the D critical that I will have here will be the same. So not spending too much time further on it. After this, the problem is symmetric with A part, but still one nice question is left, and that is, when will the initially moving electron first stop? Now, you have to sketch the trajectory, get the idea, and then comment on the result. So let me draw the trajectory in B part of the problem. First of all, you do one thing. For B, second part or the third part, randomly draw that circular motion for center of mass. Draw the motion that center of mass will possess, some uniform circular motion, somewhere center of mass is present, right? Center of mass was moving on a circle whose radius I have calculated for second part, and I think that came out to be RCM. So use that term, and even I calculated the value. It came out to be EVB by twice of M. So let it move on that circle with some omega Cm with some respective radius. Now that person is itself center of 2 points. So, I mean, one should be like whatever are these 2 points, 1 and 2, they are equidistant. So, this guy is my center of mass. And he is moving on the circle. Now, try to understand one thing. There is unique symmetry. I mean, as center of mass move down and 1 and 2 move, there's a concept. Literally, there's a factor of half between interchange of position and rotation of omega. Just observe, if one comes at the position of 2 and 2 reaches there, in this time instance, because if you gave, let's understand, if you gave velocity to one of them and you did not provide velocity to the other guy, if 1 and 2 interchange their position, my purpose is solved. That basically means that I have calculated the first time instance in which whosoever was moving with some speed will come to a state of rest. That is the right thing. Now what we need to find out is in what time will 1 and 2 interchange their position. So the point is the center of mass will move on a circle, the time period of 2 pi by omega, and as it completes one circle, the 2 electrons will only swap their position. I mean, if it is moving with omega cm or omega c, by the time he completes one circle, 1 will reach position 2 and 2 will reach position 1. Just think about that rod which is rotating about this point and let it flip. And why I'm able to make this comment is because of that factor of theta and 2 theta. Center of mass at its center. Remember, I can draw this line in a separate way. There is one line segment like this. There is center here. There is center of mass here. This line, something of this sort. And this 1, this 2, this center of mass, and this center. Again, let me repeat that here, there is no reason why I can say that center lies on this line. This is not. Circle is independent. The position of the center of the circle and the line connecting 1 and 2, the difference, I think you understand that they are not lying on the same line in this problem. Center of mass itself is moving on a circle. It's like this. If these guys are traveling some theta, then he is traveling theta. I'm randomly drawing with respect to horizontal. If this is theta, this angle is theta, this angle is actually 2 theta. He is not, the reason why I gave that factor of 2 is 2 and 1, I've written their positions. Center of mass is not, it is lying on that line, but that circle on which it is moving is not rotating about a point which is lying on that line. That's what I'm saying. With respect to center of mass, I said that 1 or 2 will possess the same motion which I have discussed earlier. That was with respect to center of mass. But this was never stated that center of mass is also moving up about a center which is lying on the line connecting 1 and 2. That was never being stated. And that is the whole catch. Even if I don't look into the geometry too much, simply by the concept that center of mass stays moving on a circle, and about center of mass, the previous motion happens, where I have analyzed that both of them will move on a circle about that point. And that point is again moving on a circle. This is sufficient to say that he is moving on a circle about some point, and about this point, both of them are moving on different radii, which are constant with respect to time. So 1 coming to position of 2 and 2 again reaching 1 is basically telling me that there is a factor of half in what? The omega of the circular motion of center of mass and the interchange of positions. If that thing becomes clear to us, then we can understand that by the time it will rotate one thing. So, like the answer will be obviously 2 pi by omega of center of mass, omega c, because as it completes one circle, as it moves by 2 pi, that theta angle becomes pi, and 1 and 2 positions will become interchanged. Omega cm expression I have already written in the previous step. In fact, anything that I am saying here is only on the basis of this equation that I have derived. Again, you can take a moment and think about it, what I have said here. That 2 factor is coming because generally, if you observe about the fixed point previously, both of them are having some thetas, and with respect to that also I am having additional theta, and the alpha b term is the same. So indirectly I am saying that that factor of 2 is coming, which is mathematically also proved. Somebody can say that how come that value is exactly same? This equation will help me in telling that. The omega that you will calculate from this equation will further help you in writing that data. So mathematically, if you solve this equation again, you should get that result, because जो circular motion हो रहा है around the center of mass, for that r omega term is actually coming out as V0 by 2. I think you understand that V0 by 2 helps me in getting a omega center of mass by 2 term. ऐसे भी बोल सकता हूँ मैं. So that factor of half is this by virtue of that V0 by 2 term. So that way also I can predict my theta, whichever way you are comfortable, or the basic mathematical equation. So whatever I have said, you give thought on each of the points, whichever way you are comfortable, you can conclude the result. And I will also suggest you to solve the further mathematical aspect of this problem. I have derived everything. All the information lies in the further analysis of this equation. You can